So we will basically start from the first question. Here we're looking at use case modeling, UML. These are use case diagrams. For example, a junior consultant can view client profiles. A senior consultant can do anything. A junior consultant can plus delete client profiles. So they ask us to show the correct actor relationship. Let's look at it this way. First, we will make an actor, a person, entity, is a junior consultant, then we have a senior consultant. There's a problem with this diagram. The problem is that there needs to be no inheritance between this. Instead, we have two functions, view client profiles, delete client profiles. Because senior partner is not the junior consultant, it is just something he can do extra. So we can give direction, he can delete profiles plus view client profiles. This is what the senior partner can do. And junior would just simply view the client profiles. So this would be one of the solutions. Another solution, if you want to do with inheritance, would be that we need to make a new person. That would be the base gets that. And the base, these two inherit him. So that would be another solution. And then he, because these two are inheriting this person, because just like we said that the senior is not the junior, we only need a father who has this, and then we can grant the rights that way. This is another solution, but I think the easier solution, number one, that I said is the best one. Then we have a second question which gives us the understanding of includes versus extend. Now we need to look for the keywords. For example, in a checkout, payment is always verified, while a promo code is applied only if. So only if and always. Look at these keywords. The customer has a valid one. Show both dependency relationship with correct arrows and everything. Now we have an actor, of course, customer. He can check out cart, verify payment details. This is something that it must happen. You must verify details. Always verified. Must include. But only if the customer apply code, extend, apply code, then only if the customer has a valid code. So while a promo is applied only if it has a valid one. So extends. So this extends go here. For example, you can apply a code. Has a valid one. So has a valid promo code can be another thing. And if you have that, only then you can extend to that shopping cart. Otherwise, if you don't have a valid one, then it will not. So you apply a code which is extending to checkout, and has a valid is also going in the same direction. Then we have primary versus external system actor. So a data engineer starts the train model use case, which relies on external AWS server, model both correctly, including non-human system. For example, we have an actor, we have a use case to train model. We can just have external actor as AWS compute server. We don't need this. This will be enough. This will be sufficient as an actor. So the operation would be this and actor. Here we learned extend and include. Here we learned actor. Now here we have a scenario, the login failure. You are writing the textual specification for login user. The user enters an incorrect password. Under which field does this belong? And how do you write this step? Now you need to know that there needs to be a login user and there needs to be a user. Text details how they work. So this is text. It's not included in use case. Use case only have actors and certain tasks they can perform. And they are based on user stories. They are based on use cases. Test case, for example, programmer did their job right. That's a test case. You can also apply this. But in this case, there is no need for all of this. This is inaccurate. Then again, this is inaccurate. Example that all of this is not the accurate way to do it. The only way would be that we have a user and then we have a certain things use cases, for example, based on user stories. Then we can look at class diagrams or UML domain diagrams. Now this diagram shows us that draw an AI agent, temporary memory buffer, and PostSQL database. Now another thing with use case diagram is that there is no technical details here. So I think that's the same for UML domain diagram, that we don't need to have technical details here. No technical details, just like we said. That's the same thing for domain model diagram. it's like it's a real world thing, but we need to understand concepts, for example. But we can use it, for example, that the memory is composition and hollow diagram for weak aggregation, each AI agent at side. So composition here is something it cannot independently live without. This can independently live without this, but this cannot independently live without this. It's a must. So for example, if we have a cupboard and it has some doors, these doors have a strong composition to the closet itself, because they cannot live on their own. They need this to live with. That's the same thing with a car. An engine cannot be on its own. It needs a car to live in. So if there's a car, there's an engine. Without the engine, there is no car. And that's the same thing with the engine to the car. So engine has a strong relationship with a car. Because if you remove the engine, what can you do with a car? And for example, car doors, if you remove the doors of the car, then car can still exist independently. Like, car doesn't vanish away, it still exists. So it's just these concepts. To be honest, even if you remove the engine, the car can still exist on its own. It's more about dependency, how certain things are dependent. Of course, yeah, in a real world, domain diagrams affect and tell us about certain functionalities. For example, let's look at another example. Here we can say 0 to many, but this is again very technical. Here we have an error relationship. It's a central halo diagram. A module may be co-taught by 2 professors. So a module, an error relationship with 1 to many professors. So now this is a good example. Look at a battery and look at a motherboard. They cannot live. Yeah, so the example was accurate. To have a smartphone functioning, if you remove the battery, there is no smartphone. Like, what is it? It's not a smartphone anymore. If you remove the motherboard, it's not a smartphone anymore. That's the same thing with a car. If you remove the engine, there is no car anymore. So engine has a strong aggregation with a car. This is again an understanding of field composition diamonds. And for this, you can understand that model a student, module, and professor. If you know that there are 3 individuals that are dependent on each other, you can create this dependency. But a module may be co-taught up to 2 professors. So if we know that a module exists the same, but one module is taught by 2 professors, the same module, TCS, is taught by Barbara and also by Kistowski, for example, then you know that 1 up to 2 professors, 1 to 2, you can write like this. So in that way, you would know that, okay, 1 to 2 professors can taught 1 module, from 1 to 2. In that way, the relationship from module is there and student is up there. This is pretty much the simple situation. Then we again go into the aggregation. Then we can look at inheritance. We know that React and VO3 are front-end frameworks. So the front-end generalization, so a hollow triangle like this is equal to a generalization. There is no need for cardinality. The generalization basically means inheritance, and there is no need for cardinalities on it. This is a domain diagram where you model the component, the VO3 component, the React component is coming from the big, so the big thing is front-end frameworks. This can be many, and this is the big bubble, and then we have VO, and then we have React and everything else. Now this goes like this on top of this like this, and this also goes on top of this like this, and we make square as entities, and then we say okay, this goes like this as a arrow. And that was it for the domain diagrams.